All right, let's talk about finite sums and approximating the area underneath curves or between curves and the x-axis using rectangles. All right, so our goal in this lesson is to formalize what we started talking about yesterday, or what we formalize what you hopefully gathered in part from the activities from yesterday. All right, remember that as we do this, that rectangles below the x-axis are negative areas. The sign, S-I-G-N, of the areas matters. We're going to label the points here. If we were in class, we'd do this sort of more together as a class. Obviously, I'm just going to treat this as just kind of a direct instruction lecture lesson type thing, okay? So what I'm trying to do is find the areas of all these rectangles. The area is going to be length times, we should say height, I'm sorry, the width times height of each rectangle. Okay, so what is the height of this rectangle? Well, it's whatever this first rectangle. We'll call it rectangle number 1. That rectangle's height is going to be defined by the function value at 0. Okay, so we'll keep that in mind. In fact, actually, we can write it down. The width of it is 2. The height of this right here is -2. So the y value right there is -2. Okay, I'll show you an easy way to get these heights quickly here in a second. Then I'm going to add the next rectangle. The next rectangle also has a width of 2 from here to here. All right, and then it has a height of whatever the function value is there. And so what I've done is I've just gone into Desmos and typed in the function as f of x. And there's two things that you can do. You can either type f of 2, and it will give you the value, or my personal favorite method is just turning it into a table. And then we don't need the negative numbers here. So we'll get rid of that. We'll get rid of this negative number here. All right, so we've got 0, we've got 2. It'll automatically fill if it senses a pattern. So at 2, we've got -2.5. We'll just go to the 10th place. It should be fine for approximating these areas. So this is -2.5 plus 2 times, and then we can do whatever that next height is right here, plus, and you just keep doing that, right? What this ends up being, actually, let's label the points here. So this is -2. And then here, this point is 2, 2.5. At 4, the height here is 0.36. Right here, the height of this rectangle, which I guess would be what, the fourth rectangle? The fourth rectangle here, the height is 1.88. So this is at 6, 1.88. And then this point right here at 8, 3.41. I guess I went with 2 decimal places there on these other ones. Anyway, so what you end up with is the area being, and there's a factor of 2 in each one of these numbers, so we can factor the 2 out in front, and then we'll just have the y values left over here. And so what we have inside the parentheses is -2 plus a -2.5 plus 0.36 plus 1.88 plus 3.41 for an approximate area that ends up being net area 2.29. Okay, so that's the net area, and it's possible for these to end up being negative, right? Because if you've got more area below the x-axis than above, then you're going to have a negative net area, okay? So let's go on to the next example. You should try the next example on your own. Pause the video, give it a try, see how it goes, and see if you can get the same answer that I do. The previous example, we used what's called LRAM. It's the left rectangular approximation method. What that is, we take the rectangles and we put them on we put the rectangle's height on the left-hand side of the rectangle where it meets the curve. So that was really poorly phrased. But you take your interval, which is 2, and then you put the rectangle, use the left-hand side of the rectangle to meet the curve. All right, so this one we're going to use RRAM. So let me show you with the same subintervals, okay? And so we're going out to 10. So we're going from 0 to 10. The subintervals, which are the rectangles, they have a width of 2. And in fact, you know what? I'm going to show you how to compute that width. So if we want to know from 0 to 10, and we know we want 5 subintervals, then our width will be the distance of the entire interval divided by however many subintervals you want. We want 5 in this case. I know that's not laid out in the instructions. It will be in the assignment and on the quizzes and things. that gives you a width of 2. Okay, so you can see here's our subintervals, 0 to 2, 2 to 4, 4 to 6, 6 to 8, and then 8 to 10. Now, if we're going to use our RAM, what we're going to do is we're going to go to the right-hand side of the subinterval, and that's where we're going to sketch our rectangle in. Okay, so that's our first rectangle here. Then we're going to go to the right-hand side of the subinterval here, and this one's sort of funky. It's going to go up to the curve here because it's the right-hand side of that subinterval, and then you're going to make a rectangle going over like this. Okay, so there's our second rectangle. There's our first rectangle. The third rectangle, we're going to go over to 6. We're going to go up to the curve here, sketching a rectangle. So there's our third one. We're going to go over to 8 and up to the curve, so that'll be our fourth rectangle. And then over to 10 and up to the curve, that'll be our fifth rectangle there. That's not a great rectangle. Let's try that. Okay. Now, you would go through, compute the y values. I already did that, so here's what you end up with. 2 times 8.54 plus 3.41 plus 1.88 plus 0.36, and then plus a negative 2.5. And you can write that as minus if you want. You don't have to write it as plus and negative, but that just reminds us that we're summing all of these. And then finally you get an area that is 23.38 square units. Okay, that is our RAM. We use the right-hand side of the subintervals. Okay. Now compute the area from 0 to 10 using 5 subintervals and MRAM. MRAM stands for middle rectangular approximation method, and this is going to land us in the middle of the subintervals or the middle of the rectangle. Okay, so I got the same curve again. We're going from 0 to 10. I tried to add the lines in here at intervals of 1 so we could use the middle. So here we go. If we're going to go subintervals of width 2, again, because 10 divided by 5 is 2. So we've got a subinterval here. I'm sorry, we have a subinterval here from 0 to 2, then 2 to 4, then 4 to 6, then 6 to 8, and then 8 to 10. Now the first rectangle will go based off of the middle of the first subinterval, which will be here at 1. Okay, so we'll kind of track 1 lands right here, and then we sketch in our first rectangle. Like that. So there's our first rectangle. Okay, then we'll go to the next one. Subinterval from 2 to 4. The middle of it is at 3. So we sketch in that rectangle. I'll pause right here, and so the height of this, and just say that the height of this rectangle is going to be whatever the function value is at 1. So this point is f1 comma f of 1. So you'll figure out what the function value is at 1 there, right? Then same thing, similar process here. So it would be 3 comma f of 3 for that point. Then we're going to go from 4 to 6. The middle is 5. So we sketch in a rectangle there. Six to 8, we're going to go to 7. That's the middle. Sketch in a rectangle there. And then from 8 to 10, the middle is 9. So we sketch in the rectangle there. And there's our 5 rectangles. Okay, so then you go through and you compute all of the heights. What you should get, again, the width based on what we got there, or what we were given, would be 10 over 2, which is, sorry, 10 over 5, which is 2. And then the area is going to, actually use the other pen, A is going to be negative, 2 times negative 2.74 plus a negative, so minus 1.24 plus 1.46 plus 2.24 plus 5.69. I guess last year I used the 100th place, or 2 decimal places. I think 1 is probably fine for your approximations. You end up with an area of 10.82. Okay. So that is the process for sketching in the rectangles and finding approximations using LRAM, RRAM, and MRAM. On the back of the note sheet, or the second page of the note sheet, it kind of lays out the three explicitly here, kind of a nice sketch on each one. Notice that LRAM in this example that they've sketched here is an underestimate. But if this curve was shaped differently, so if it was maybe going down like this, then LRAM would be an overestimate. So it's not that LRAM or RRAM or MRAM, for that matter, is always an under, over, and over. It depends on the shape of the curve. Okay. So the last thing here, suppose a particle starts at x equals 0 and moves along the x-axis with velocity given here. Where's the particle at t equals 4? All right, we're going to use MRAM. So what this turns out, the way that we approach this, is if we put velocity on the y and we put time on the x. Let's sketch this out just kind of generally here actually. So if I have, let's say I just have a straight line for my curve. Okay, again I've got time and velocity here. Let's say this object, whatever, moves for, and this is, by the way, this is separate from the example. So let's say that this, goes from 2 to 6 seconds, and it's always been the same velocity, which is 10. Okay, and you want to know, well, all right, so this object goes 10 meters per second, let's say, for 4 seconds. So how far did it go? You'd be like, oh, well, it's just 10 times 4. It went 40 meters in that case, right? Well, it turns out that that is the same as the area underneath of that very, very simple velocity curve, which is just a line. Okay, so if our velocity curve is squiggly, we can still use that same principle to figure out the displacement or the total distance traveled of the particle. So in this example here, if you're given a velocity function of t squared plus 1, and you've got a picture of the graph, which is not a great picture of the graph, but you've got the graph here, what you can do is you can find the area under the curve, and that will tell you approximately how much the displacement, or how far the particle has traveled. So we're at 1, 2, 3, 4. So 4 is going to land us somewhere up here. So there's our interval. I'm going to regret drawing that line probably. I'm going to take it away because we're going to use MRAM here. So let's figure out what the width of our rectangles are going to be. The width is going to be, oh, I guess I didn't give you the, let's use 4. So 4 rectangles and a distance of 4. So our width will be 1. Okay, so we've got a subinterval here, 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 and here. And then we're going to go use MRAM, right? So we've got this here at 0.5. We've got here at 1.5. We've got here at 2.5. Here at 3.5. And that's how we would sketch those rectangles in. There's four of them there, right? So when we sum these areas, this will give us an approximation of the distance traveled by the particle. I don't think we need to go through and do the computations. It's sort of monotonous to do, and I'm not sure that we need to extend the video any longer than it already is to do that. But the area of these rectangles will give you an approximate distance traveled by the particle. And that's it for section 6.1, LRAM, MRAM, and RRAM using the rectangular approximation methods.